We're going to take a closer look now at the connection between electric potential and the electric field. Because of course they have to be related, right? The electric field is related to the force. The electric potential is related to the electric potential energy. And we know that force and energy are related, right? Last semester we talked about how gravitational force changes gravitational potential energy. The roller coaster problems, where high gravitational potential energy changed into kinetic energy as you went down the hill, and then back into gravitational potential energy as you went up the next hill. So forces and energy are related through work, right? Work changes the kinetic energy of an object. Work is related to the force of an object applied through some distance. So how are electric potential and electric field related? Well, the electric field is related again to the electric force, and that is a vector. Electric force, like all forces, have a direction. So many newtons down or up, left, right, north, south, whatever. The direction is important, right? If your car runs out of gas, you want to get behind your car and push forward, not on the side of your car, pushing the car to the side. That doesn't help very much. The electric field, since it's related to the electric force, is also a vector. Direction is important. However, the electric potential is related to the electric potential energy. Those are scalars. Energy is a scalar, kinetic energy, potential energy. It does not matter what the direction is. A car traveling 75 miles an hour north has the same kinetic energy as a car traveling 75 miles an hour south, right? The same speed, the same mass of the car gives you the same energy. So here we have this setup. Now I've rotated this 90 degrees. This is more consistent with what your book shows, but it's the same setup. You have a positive plate and a negative plate separated by some distance d. There is an electric field that is established between these two plates. Again, this simple thing is called a parallel plate capacitor, which we'll talk about later on in this lesson. So the green lines show the electric field. The electric field is constant. It's uniform inside those plates. Again, electric field, it's all pointing in the same direction. It's all pointing from positive to negative. So electric field lines are pointing to the right. And they're evenly spaced, showing us that the electric field has a uniform strength between those plates. If I drop a free positive test charge in between these plates, it's going to want to accelerate to the right. So this plate on the left, we'll say, has a potential of V sub A. Whatever this is. It might be plus 12 volts, plus 20 volts, whatever. V sub B is over here on the right. That has a lower potential because it has negative charge versus positive charge. So this might be at 0 volts or minus 10 volts, minus 20, whatever. This might be at 12 and 6 or minus 6 and minus 18. One is going to be higher than the other, but they're just going to have a given value. So the change in potential between these two plates, when the positive charge is dropped in on one side and moves to the other, this positive charge will experience a change in potential, VB minus VA, final minus initial. Well, the negative change in potential then, multiply the top equation through by minus 1, I can rearrange it and say it's V sub A minus V sub B, or I'm just going to call that V sub AB. That's the potential difference between these two terminals. For a 9-volt battery, it's 9 volts. That doesn't mean that one terminal is at 9 volts and the other terminal is at 0 volts. You can set up a circuit where the lower terminal is at 3, the upper terminal has to be 9 volts higher, so it would be at 12. The difference between the terminals of a 9-volt battery is 9 volts. Well, the work is equal to the negative change in potential energy. Right? We learned that last semester when we talked about work and potential energy. Well, the potential energy, the electrostatic potential energy, is the electrostatic potential times Q. Well, we have negative delta V here. We know negative delta V is equal to VAB. So I'm going to make that substitution and flip the terms. So the work is equal to Q times the difference in the potential. If we have a uniform electric field, it has to be uniform for this next step to work. The electric field is related to the change in potential, right, the electric potential between the two terminals, divided by the distance between those terminals. So if I know VA and VB, if I know there's 9 volts between them, or 12 volts, or 20 volts, or 100 volts, or 5 microvolts, or whatever, if I know the difference in voltages between those two terminals, I divide it by the distance I've separated these two terminals at, that gives me the electric field. Again, only if the electric field is uniform. If the electric field is uniform, this equation is no longer valid. It actually requires calculus to do, which is beyond the scope of this class. So I can rearrange this equation and say the potential between 2 points is equal to the electric field times the distance between the terminals. So I can relate the electric field and the electric potential using these two equations if the electric field is constant. And almost all the problems you'll get in this class, the electric field is constant for these types of problems. Now, so the general rule is the electric field strength is equal to the negative change in potential. Remember, VAB is the negative change in potential for this problem. The negative change in potential over delta S. Delta S is just a placeholder that could be delta X, delta Y, or delta Z, depending on what direction you're going. Delta S is just the distance over where the change in potential delta V occurs. So if a change in potential of 10 volts occurs over 1 meter, this would be negative 10 volts over 1 meter. If the change in potential is 3 millivolts over a centimeter, then it's negative 3 volts over 1 centimeter. So this relates the electric field and the electric potential.